Today I'll be showing you how to make a DC motor using simple parts. First off, we'll be talking about wires. The wires will be used to make things like coils and stands. As you can see, things like this. Alright, for the coil, you need a coil to see whether it is cutting whether it is spinning, and use a marker to draw across. This will allow insulation. This is the wire cutter, where you use to strip and cut the wires. Simply stated, this is the current source. You produce the current necessary. The marker you need. The magnet, which produces the magnetic field. And lastly, the thing that holds everything together, along with the holder.
Now I'm going to show you how to set up the DC motor. Firstly, now we have to make the coil first. Yeah, this is how you actually make a coil. Yeah, then the final product will be actually this. The ends will be stripped off, and however, for the ends, right, half of it will be insulated with a marker, as shown.
The reason why we insulate the coil is so that it will not come to a point where the coil's magnetic field align with the magnet's magnetic field. When they are aligned, attraction will occur and the motor will stop moving. The circuit is periodically broken to allow on-off of the circuit during the rotation. At a point when the circuit is broken, there is still momentum to allow the coil to rotate until it completes the rotation.
And now we're going to set up the DC motor. First, we're going to attach the wires to the plastic container as stands. Next, we're going to put a magnet on top of the container. And then we're going to put a wire coil on top of the stands. Before we start, ensure that the blackened area is facing on top of the DC motor. And then lastly, connect the load to the setup.
By connecting a battery to the circuit, current will flow through the armature. The direction of current flow is shown on the picture. The magnetic field of the permanent magnet is directed from the north pole to the south pole. A force is generated by the interaction between magnetic field and current. The generated force will then produce a torsion. The torsion will then help to turn the armature.
In order to determine the direction of force, Fleming's left-hand rule is applied. Fleming's left-hand rule states that the middle finger denotes the current from the positive end to the negative end. It's perpendicular to the direction of magnetic field, which is denoted by the index finger from the north to south pole, and both components are perpendicular to the direction of force, which is denoted by the thumb.
The diagram above shows the setup of a simple DC motor. The direction of current, which is denoted by the black arrow, will flow from the positive terminal of the battery to the negative terminal of the battery. The current will pass through the entire circuit, which includes the wire coil. The current flowing through the wire coil will be in a circular-like motion, and the current will flow from the left to right on the upper end of the coil, and current will flow from right to left at the lower end of the coil. The direction of magnetic field from the north to south pole will be facing upwards towards the magnetic coil. Therefore, by using Fleming's left-hand rule, results can be seen on the diagram above. As shown on the left-hand view of the setup, a force which is produced on the upper end of the coil, will push the upper end of the wire coil to the right. Another force, which is produced on the lower end of the coil, will push the lower end of the coil to the left. This will produce a clockwise moment and will result the coil to constantly turn clockwise.
Applications of a DC motor are normally high in power, lightweight, small in dimensions. This is because PMDC are simple and affordable. They are favorable in automotive industries. So some real-life applications are like pumps, fans, electric wheelchairs, elevators, satellites, and power tools.